Imagine drawing a line on a computer. Today, doing so comes so easily to computers that we don't ever think about the fact that basically every line we see is some sort of an approximation of the original. Of course, the lines today also use other algorithms to make them look smooth and pretty. Think of anti-aliasing, for example. But today we'll be discussing the most important one, called the Bresenham's line algorithm, that was written by Jack Bresenham back in 1965 for a digital plotter, but then adapted for use on screens later on. In this video, we will be covering the original algorithm made for digital plotters, as the logic behind it is simple yet genius, and hasn't changed after adapting it to screens. Let's say we want to draw a line using a digital plotter. For simplicity's sake, let's say that it's possible to draw this line using only the instructions move to the right or move diagonally along this grid. Further in the video, we will explain how other cases work as well. For now, let us stick with this situation as an example. Let's call the coordinates of d1, x1, y1, and those of d2, x2, y2. In our case, we can only move from one grid intersection to another, so how do we make the best approximation of the line using our given toolset? Firstly, for ease of use, instead of using absolute coordinates, let's use relative coordinates a and b. Here are a couple of changes we will do with that coordinate system to make our lives easier. We make the coordinates of d1 0, 0, so that d2 has the value of delta a delta b, with delta a being equal to x2 minus x1 and delta b being equal to y2 minus y1. This means that the line d1 d2 has the equation of b is equal to m times a, with m being equal to delta b divided by delta a. The integer values of the coordinates correlates with the points that our plotter can physically go to. But note, we are assuming here that d2 will be on the grid. Otherwise, we have to approximate d2 so that it is located on the grid. Let's say that for the first movement, the plotter went diagonally, and for generalization's sake, let's call it P and give it coordinates a1, b1. Let's call the points where the digital plotter can move to R and Q for horizontal and diagonal movement respectively. Let us also define a point S as the intersection of the original line with the grid. The question then becomes, how do we make a decision regarding what point, either R or Q, we should go to? We want to make as good an approximation as possible, meaning that the point that we can go to, R or Q, has to be the closest to our original line. For that, we have to draw perpendicular lines from R and Q to the original line, and let's call the segments that were created small r and small q. If we were to know how long those segments are and compare them to each other, we can find out what point can make a better approximation and go to that point. There is a problem with that approach, however. It is incredibly difficult computationally to find the distances r and q. To calculate distance from a point to a line, you first have to make a new line that is perpendicular to the original line, then adjust its formula so that it also intersects our point, and then use Pythagoras to find the distance between the point and the intersection of the two lines. All of that takes precious compute power, and that's why we need a different way to compare R and Q. The first optimization we can do is, instead of looking at the absolute values of R and Q, we can look at the difference of R and Q. If R is bigger than Q, then the value of R minus Q will be positive, and in that case Q is closer, and so the plotter has to go to that point. And on the flip side, if Q is bigger than R, then the value of R minus Q will be negative, and in that case R is closer, and the plotter has to go there. When R minus Q is 0, it doesn't really matter what point to go to, as R has the same value as Q, but as a corner case, let's say that in that case the pointer moves diagonally. Let's also replace R minus Q with the symbol nabla so that it is easier for us to refer to the value that decides our movement. Now we are done with defining and can get to solving the actual problem. You might have noticed that the intersection of the line we are trying to approximate and the grid has created two pairs of angles of the same value. We only care about this one pair though, because by drawing the segments R and Q that are perpendicular to our original line, we have created two right triangles whose angles are the same. This means that we can compare the sine values of the similar angles to come to a relation that replaces R and Q with QS and RS. Instead of using QS and RS every time these segments are mentioned, let us call them Q' and R'. For one thing, we can calculate the values of R' and Q' with a lot less effort because both of these values are just differences in the vertical coordinates of different points that we can also easily calculate. The coordinates of different points we can also figure out with basic arithmetic, because we have earlier agreed that the coordinates where the plotter can go to are integer values. We can find the coordinates of R and Q in respect to P, which we have given a coordinate of A1, B1. The plotter has to move one unit to the right no matter what, so we can fill in that the horizontal coordinate of both points should be A1 plus 1. As for vertical coordinates, R has the same one as P, while Q has the vertical coordinates of 1 bigger than P, meaning each coordinate is B1 plus 1. As for S, we can find its horizontal coordinate, which is the same as Q and R, A1 plus 1. But when it comes to the vertical coordinates, we will have to do some more work. We have earlier said that the point S is the intersection of the original line with the grid. And we have also assumed that the line has the equation B is equal to m times A, with m being equal to delta B divided by delta A. In our case, A is the horizontal coordinate and B is the vertical coordinate. In case of S, we know its horizontal coordinate, and delta A and delta B are always given, meaning that with some manipulation of this equation, we can find the vertical coordinate of S. Knowing all these coordinates, we can find the value of Q' as the difference in the vertical coordinate of Q and S, and similar can be done to R', as it is the difference between the vertical coordinates of S and R. Using this information, as well as the identity we've proven previously, is there a way to find a relation between R' and Q' that will function as our nabla? The first thing we can do is to try to compare the division that we have in the identity that compares R, Q, R' and Q' with the subtraction that we have in the formula for nabla. It comes intuitively that R minus Q is bigger than 0 when R is bigger than Q, and vice versa. If you were to try and fit some sort of division to the same conditions, one of the solutions that you could have come up with is the following. R divided by Q will be bigger than 1 if R is bigger than Q, and vice versa. To compare with 0, we will subtract 1 from R divided by Q. The nice thing for us with this formula is that we can use the identity we have proven earlier and replace R divided by Q with R' divided by Q'. We can further manipulate the equation to get R' minus Q' divided by Q'. Division doesn't change the sign of the expression as long as you don't divide by a negative number, something that Q' can never be, as it is by definition a distance from one point to another, and distance cannot be negative. That means that sign-wise, R' minus Q' all divided by Q' is the same as R' minus Q'. Looks eerily similar, doesn't it? The condition we have just created is almost exactly the same as we started, only now we have replaced R with R' and Q with Q'. Funnily enough, the condition we have started with is the same as our decision-making algorithm if you were to write out nabla's definition. Because of this, let's redefine nabla as R' minus Q'. Because we already know the values of R' and Q', let's further rewrite nabla. Additionally, let's find a common denominator and put everything into one fraction, and as you can see, that results in the following expression. We want to have as little division as possible, as it is more computationally expensive than subtraction or addition, so to avoid it, let's once again redefine our nabla as delta A times R' minus Q'. Writing that out only in terms of the coordinates of the previous point chosen and delta A and delta B, we get this equation. Instead of using A1 and B1, let's rewrite the indices to make everything look a bit more like computer code rather than some maths. Here, I is an integer that goes from 1 all the way to delta a and indicates the index of the iteration. We can also replace I with I plus 1 to use in the future equations. Let's imagine that the value of I is 1. We start at 0, 0, which we can put into the equation of nabla by setting the value of a with an index of I minus 1 and b with an index of I minus 1 to 0, and calculate a first nabla in the sequence. Our expression simplifies quite a bit, leaving us with nabla 1 equals 2 times delta b minus delta a. Knowing this, we can focus on figuring out a recursive relation between our nabla and its following iteration. To do that, we need to find the relationship between our current coordinate and the one we came from. If we have just moved diagonally, it means that the current value of both coordinates will be bigger by 1 in comparison to the previous point. And if we move horizontally, that happens only for the horizontal coordinate, and the vertical coordinate stays the same. This information is useful to us because the definition of nabla is directly tied to the direction of movement. If nabla is bigger or equals to 0, the plotter has to move diagonally, and if it isn't, then the plotter has to move horizontally. This means that we can substitute diagonal and horizontal movement with the sign of nabla. After doing that, let's look at every condition separately. We already know the relationship between the current coordinate and the one that came before it, and we can fill that information into the equation for the nabla that determines our next move. We can further simplify the equation to see something interesting pop up. After some rearrangement, we see that a big part of the equation is just the value of our current nabla, so we can substitute this whole part for nabla I. And the same can be done for the other condition, only now, because we don't add 1 to the vertical coordinate, we don't have minus 2 delta A in the equation. There is a problem, however. The formula we have just defined only works for movement to the right and diagonally. What about the other directions? Well, we already have a well-working algorithm for one direction, so we can try and adapt the formula that we have, and it is easier than you might think. Because we have defined a different coordinate system, we can change the directions and the positions of A and B to keep the equations correct. Here is a table of such coordinate systems and the corresponding possible movements m1 and m2 in different octants, directions where the second point is if taken the first point for the origin. For example, the first octant portrays a situation we were solving the whole time, and we only have two choices of movement, m1 and m2. If nabla is lower than 0, we move to the direction of m1, and if it is bigger or equals to 0, we move to the direction of m2. Finding the fitting coordinate system for a certain direction is done through mirroring and rotating the original situation to fit the desired octant. How do we figure out in which octant we are though? That we can also easily determine by looking at three things: sign of the change in x, sign of the change of y, and the sign of the difference between the absolute values of the two. Through that, we can determine the octant we will have to move in and what value delta A and delta B must take. And with this, the algorithm is finished. Humanity has advanced quite a way since the 1980s when it comes to computer graphics, yet this algorithm has stood the test of time and remains an important part of creating digital images, whether we are aware of it or not. We hope you enjoyed this video. There will be a couple of useful links regarding the topic in the description.